My name is Isaac Mitchell, and this talk will be about the binding of a gold atom within a double vacancy in a graphene sheet. The purpose of this is to just start understanding how binding energies work, why you might do them, how you would calculate them, and what they are the precursor to in your work as a chemist. So let's start by explaining a little bit about binding energies. Let's assume that we have a chemical reaction taking reactants and going to products with the stoichiometries M for the reactants and N for the products. The binding energy is a determination essentially of the stability, and it can be calculated as the sum of the energy of the products minus the sum of the energies of the reactants times by their stoichiometries. This is a precursor to a lot of the thermodynamic properties, so Gibbs free energy or Helmholtz free energy will rely on additions of enthalpy and entry contributions, and from these the relative concentrations of different species can be found. It's usually one of the first things and one of the simplest things you can calculate as a computational chemist or a computational physicist in this area. We today are going to look at the binding of a gold atom into a double vacancy in graphene. These sorts of systems are often used in single atom catalysts or just to pattern sort of the surface of graphene. So we will be calculating the binding energy essentially to figure out the stabilities of these systems, see if it's actually stable to do this. So what are we going to be calculating? First, we have to calculate the energy of a graphene double vacancy. This is where we've removed two carbon atoms from the center of a graphene sheet. We also need to calculate the energy of a gold atom within the vacuum. Then we'll have to combine the two and place the gold atom within the middle of that vacancy, and then we will have to calculate the energy of this. This will usually involve a actual optimization step, so you can't just calculate the energy directly. It needs to be optimized, and final energy will be what you use. In this case, because it's set up like this, the stoichiometries are 1 to 1 to 1. One vacancy per one gold atom give one gold atom within a vacancy. So the energy of binding is fairly simple. It's just the energy of the double vacancy plus the gold atom minus the energy of the double vacancy minus the energy of the gold atom. And this is possible because it's 1 to 1 stoichiometry and there's no change in the number of atoms going from each thing. So the number of atoms within the first two is the same as the number of atoms in the final product. Tools we are going to be using. First, we're going to be using the atomic simulation environment, ASE. It has extensive tools for building molecules and crystal structures, so we will be using it to build our graphene double vacancy and the gold atom within that vacancy. It also has extensive optimization tools that can be used to optimize structures using input forces and energies, but it can't do it itself, so it needs a driver or a calculation tool to do that. And today we'll be using the hotbit methodology. Hotbit is a simple density functional type binding code, or DFTB code. DFTB itself is a simplification of DFT methodologies that is much faster, but also has a cost to the accuracy and a cost to the generality. So parameters need to be built to get this to work. Hotbit is interfaced with ASE, so ASE will call it to get the energies and forces it needs to optimize these structures. So let's get through the prerequisites. Everything will be built in Python. This is a Python script. ASE, Hotbit, and NumPy need to be loaded in so that you can actually use them as a part of these calculations. It is generally good practice to be consistent between different calculations. This is to ensure that the energies as you go through represent the same thing essentially. So you need to have the same cutoffs, the same K points, the same methods used. You can't just use DFT calculations then use DFTB on a different thing. They give different energies. You need to ensure that when you're doing these kinds of periodic systems, that the vacuum layer between different images and the distance between different images in the XY plane are also far enough that they don't interact, or they will contribute. So these systems need to be large enough. It's also noteworthy that both hotbit and ASE use angstroms in their calculations and electron volts for the units of energy. And while this is fairly normal, if you are using a different code, you need to keep this in mind if you're converting from one type to structures that use, say, Bohr or Hartree to another that uses, EV and angstroms. So first, let's construct the double vacancy structure. First, we construct a simple unit cell of 2 carbon atoms using the atoms function within ASE. We repeat this function out. In our case, I think we did 5 by 5 or 3 by 3, 5 by 5, I think it is. We repeat this out. We then use the delete atoms function to delete 2 of the atoms, the first 2 atoms in this. These first 2 atoms should be the ones in the lower left corner, so they're the first 2 atoms. If not, you will need to use, if the indexing is a bit messed up, you'll have to use a sort of an area function to remove this. ASE can be a bit difficult removing atoms. It's very easy to add them, not so easy to remove them. The next step is we rattle the atoms. We essentially move them in random directions ever so slightly. This is to prevent the optimization to saddle points, and then we write out our initial structure so we know what we're starting with. The optimization, we use the FIRE algorithm. First, we make a calculator using hotbit. We're not using self-consistent charge this time around. Accuracy would increase using self-consistent charge, but so would the time these calculations took, and I'm running this on an extremely old computer. I can't do this with DFT. I can do it with DFTB with no self-consistency charge, which is one of the benefits. K-points is defined as the same for all the systems that we're going to run, which is 5 by 5 by 1. Generally, when the system is long enough in certain directions, the sampling in the reciprocal space can be lower. So you might only need a 1 1 1, but here we're using a 1 1 5 5 1 in the direction of the graphene sheet, and the 1 is just in the vacuum direction. We define a dynamics calculation using the FIRE optimizer and attach it to the structure. We run it, and that gives us our final energy and our final structure. Now, what it looks like is this. As you can see, those two pentagons have attached, and now you have the bond between them, and you have an 8 carbon ring in the middle. Gold atom is very simple. The gold box is very similar. You have to make sure that when you're building these, that things stay consistent. So the size of the box needs to stay the same, and where you put the gold should be the same spot where it will be in the final structure. In these calculations, it's not so stringent that you need to do this, but when you go to a different sort of methodology, such as a plane wave methodology, then you need to make sure that it's the same. That's the reason why the ratios are 1:2R, and the lengths are L times R. So the R is the repeat, how many times we repeated the graphene sheet, so we repeat it out here as well in another way. We then define hotbit, optimize it, and that gives us our final energy. Now we've got to construct our gold double vacancies structures. Here we build our double vacancy the same way. We build our gold the same way, and then we use the append function to add it. And given the way that we built our gold structure before, this should add exactly where that double vacancy was. If it doesn't, you need to go to more advanced methods with an ASE to do this. We rattle to prevent optimization to saddle points. We then use hotbit and FIRE to optimize these structures, and that gives us our final energies. And if things have been done consistently, you shouldn't have any mistakes with this. So yeah, this is what optimizes. It actually breaks that the carbon atoms move away because it's such a large atom, that gold atom. So now we've come to the end. We can actually calculate our binding energies. So we can do this. If you run the example code that's been given to you, you should get this as an output. About -7.5 EV, which is a fairly strong binding, so which is sort of expected. The carbon atoms do not like being unbound. It's also noteworthy to remember what the energies you're working with are. It's no use just having these numbers. These need to be specified as being in EV.